Happy day and welcome everyone. Today we're going to be talking about Avogadro's law and the ideal gas law. So up to this point, we've ignored the amount of gas and we've worked with three variables. If you think about the combined gas law, those variables that we've been using so far are pressure, volume, and temperature, PV and T. Now let's consider a very important variable, the amount of gas in the system that's expressed in moles. And for moles, we use the symbol of lowercase n. So Amedeo Avogadro, who lived in the early 1800s, late 1700s, he interpreted Gay-Lussac's observations and came up with what is called Avogadro's hypothesis. And what he said was, equal volumes of gases at the same temperature and pressure, now this is important, that our volumes are equal and the temperature and the pressure are the same, then they should have an equal number of particles. And when we say the word particles, what we're typically referencing is either atoms or MOLC molecules, okay? Either one of those. Therefore, what's true? Well, if you know that the number of particles are the same, then your moles of gas should also be equal. So this is really cool because it's kind of putting all of these variables together to kind of give us a number that we can use in calculations. Okay, so it says, imagine that we have these four balloons here, and these are all at 22.4 liters at STP. Oh wait, that sounds familiar. Do you remember when we were doing conversions? If you had 22.4 liters at STP, how much did you have? If you said 1 mole, you are absolutely right. Then what that means is, as long as all of these have the same volume, they're at the same temperature, and they are at the same pressure, then we know that they have equal moles. And if it happens to be 22.4 liters at STP, we have 1 mole. And so what we can do is we can basically use ratios in order to be able to calculate if we do change one of those things. And we can very easily do this. So if these are all at 22.4 liters, what's the mass of each balloon? Okay, well, if it's a mole, then do you know how much a mole weighs? Well, that's not constant. Are you thinking we need to go to the periodic table? Well, you're right. All we need to do is look at the molar mass on the periodic table. And so we know that for helium, it's 4 grams per mole. Oxygen is 16, but times 2, so 32.00 grams per mole. For NH3, if we want to know how many grams are in a mole, nitrogen is 14.00, and each hydrogen is 1.01, so then we should get 17.03 grams per mole. And we know that water is 18.02 grams per mole. Okay, now the next question is asking, what about particles? So the atoms or the molecules that are in each balloon. Well, if you know you have a mole, how many particles do you have? Well, we know that 1 mole is always equal to, what's that long number? 6.022 times 10 to the 23rd. And remember, it can be anything. Just like a dozen is always 12 anythings, a mole is always 6.022 times 10 to the 23rd anythings. Okay, now, the only thing is that I want to make sure that you remember is that it could be for any one of them. So sometimes a misconception that students will have is they'll say, oh, but if it's oxygen, it's O2, so I need to double it. Wrong. They're asking us how many of the O2 particles are in there. So if I counted how many helium atoms, how many O2 atoms, how many NH3 molecules, well, they would all be 6.022 times 10 to the 23rd. Okay, so that's kind of the beauty of what is Avogadro's law. Okay, so his law then followed that we said, just similar to what we said, the volume of a gas, as long as you're at constant temperature and pressure, is directly proportional to the number of moles of gas. And so then what we can do is we can come up with an equation. And so we know that V over N equals V over N, or V over N is a constant. We can also write this as V1 over N1 equals V2 over N2. And now we have an equation that we can use. So again, as long as your temperature and your pressure are constant and you're simply looking at volume and moles. So let's take a look at that. And by the way, there's a little bit of a side note in here about Avogadro's number. That was not actually discovered by Avogadro. So his law is what he did. So there were others that were involved in that. Let's take a look at a simulation to get an idea of how this would work here. Okay. So what I did was I added some moles of gas into here, so I can see I just have some heavy heavy particles in here, and I'm setting the pressure constant, okay? And so what I'm going to do is I want to check to see if the pressure is constant, what happens to the volume if I add more moles in? Well, it makes sense. It's almost like if you were to fill a balloon with more air. Well, because it has a flexible, your container is flexible, then it'll get bigger if you add more air in, okay? Well, what happens if I open this up and I let some of the air out? Let's see if we can let some of the air out. There we go. Some of the air is going, there we go. And now it's getting smaller, okay? So again, as we increase our number of moles, then our volume ends up increasing, and so we say it's directly related. But if we were to get rid of some of those moles, let some of them out, then, and now again, what we're trying to do is we're trying to hold the pressure constant, okay? So we're trying to keep the pressure constant and the temperature constant so that your volume will increase or your volume will decrease when you let some of it out, okay? All right. Then the value of 22.4 liters per mole is established as molar volume. That's always just simply referencing that we have liters per mole. Whenever they say molar volume of any gas, that's what they're looking for. Atoms, molecules, mixtures at standard temperature and pressure, which we know is 0 degrees Celsius and 1 atmosphere. But the issue is STP isn't a common lab condition. If it were 0 degrees Celsius in here in this lab room right now, I'd be wearing a coat, okay? So it'd be freezing. And 1 atmosphere, yes, that's sea level. We're actually a little bit higher than sea level here in West Bloomfield. So scientists needed to come up with a way to calculate the approximate amount of gas at other temperatures and pressures. And that's why or how we end up using or coming up with the ideal gas law. Okay. So question 10 simply says, if a runner inhales and her lungs are filled with 0.15 moles of air with a capacity of 4 liters, so we've got 0.15 moles, this is what we're going to call N1, and our V1 is 4 liters. How many moles? So what we're looking for is N2 is what we're looking for. Should she have when she exhales if her lung capacity reduces to 3 liters? Assume all other factors remain constant. Okay, so all we're going to do here is we're going to simply use our equation of V1 over N1 equals V2 over N2. So go ahead and plug in and let's check to see if you came up with the same answer. Did you get 0.11 as your answer? And that would be 0.11 moles. Okay, so let's take a look at this. Now remember, easiest way, you do your cross multiplication, you start opposite your unknown and multiply. So I did 0.15 times 3 and then I divided by 4. So you always divide by what's attached. Don't even write anything else besides that down. And I got 0.1125, but that's 4 sig figs, so I reduced it down to 2, and I got 0.11 moles as my answer for that, okay? And so again, if we see that the volume decreases, then our moles should be decreasing as well. Okay, now we're doing our ideal gas law here. So ideal behavior depends on certain conditions, and basically the scientists calculated a constant, or an ideal, using the information that 1 mole occupies 22.4 liters at STP. And when these values are filled into our combined gas law, we get what they call R, the ideal gas constant. So if we were to multiply these numbers together, then what we should get is 8.312 as our answer. Okay, and now what we're going to do is we're going to switch our pressure unit, because remember, the only difference between our R values is going to be what unit we can use for pressure. The volume is always going to be in liters, temperature is always going to be in Kelvin, and our amount of gas is always going to be in moles. So make sure you're not in grams, make sure you're always in moles. And be careful with milliliters, because in labs, we typically use milliliters, and so you're going to need to convert to liters in order to do the calculation for ideal gas law. Okay, so if we're switching it to atmospheres, to ATM, like it is right here, well, I know that it's 1 atmosphere, and so instead, I'm going to do 1 times 22.4 divided by 273, and when I do that, I get 0.08206 as my answer for that, or 0.0821 is what sometimes is used as well. And then if I want to switch it to torr, well, I know that standard in torr is 760. So on this one, I'm just going to do 760, multiply it by 22.4, and divide it by 273, divided by 1. I'm getting 62.36. Usually they'll use 62.4, but 62.36 also works. So 62.4 is very typical on this one too. Okay. So if you rearrange the equation, and by the way, you won't have to do this. You'll be given the constants. You just need to convert sometimes or use a different R value if you need to use if you have a different unit for pressure. Okay, so if you rearrange the equation, we get PV equals nRT. And so instead of solving for this gas constant, which is looking like our combined gas law, instead we're going to use Pivnert. Okay, so we usually call this Pivnert, the ideal gas law. And so we can see the different R values. So again, if you're using kPa, you should use the 8.31, atmospheres and millimeters, which is the same thing as torr, millimeters of mercury, okay? Which is the same thing as torr. Okay, so this equation permits you to solve for the number of moles, or you can solve for anything else, but I'm going to tell you that a lot of times you're asked for the molecular weight of a gas, okay? So how do we calculate molecular weight? I'm going to show you that in just a second. Well, we know what the units are, so we'll come back to that in just a second here. All right, so let's try question 11. You fill a steel cylinder and it has a volume of 20 liters, so that's going to be our V, and it has a particular gas. We know our pressure, so there's our pressure there, 28 degrees Celsius. Remember, we always add 273 to that, and so we know that we're going to get 301 in Kelvin. All right. And so the first question is, how many moles of gas does this contain? So I know I'm looking for N, okay? Now, how do I know I'm not using combined gas law? Well, combined gas law gives me two situations. I don't have two situations. I don't have two volumes or two pressures. So they're simply asking me for moles. So I know I'm just going to use the ideal gas law, which is PV equals nRT. Some people like to solve for N before. I usually don't. I typically just go right ahead and start filling my numbers in, and then I do my algebra. So go ahead and fill that in, and let's see if you get the same answers I do after you divide. Did you get 160 decimal point moles? If you did, awesome job. So one of the things that people always say is, I'm not sure what I'm supposed to do for R. How am I supposed to pick that out? Why did I pick the 8.31? You want to make sure your units all cancel out, okay? And so once I fill this in, I want to double check it. So I can see here that my Kelvin is going to cancel out with my Kelvin right there. I can see that my kPa will cancel out with my kPa if I divide everything over to the other side to get N by itself. And my liters will cancel out with my liters. And so what I'm left with is divided by moles, which is actually moles as your final answer. So when I do in my calculator 2E4 times 20 divided by 8.31 divided by 301, I actually get 159.9, but because it's 3 sig figs, then my final answer is actually 160 with the decimal point moles. Okay, so that's the first question. The second question says, you weigh the cylinder and you find out that the cylinder weighs 4,480 grams. What's the molecular weight? Well, we know that molecular weight is in the units of grams per mole. Okay, let's see if you remember this. You put your arm out and say grams. Other arm out and say moles. Divide grams over moles, okay? So if it's unknown, that's when you're going to want to do this, okay? If it's something known, I'm just going to go to the periodic table and I'm going to use a bridge, okay? But otherwise, if you don't know what it is, grams, moles, grams over moles, just like when we did moles, liters, moles over liters, okay? Or there were other things that we've done this for as well. Okay, so how many grams is it? Well, they told us in the problem that it's 4,480 right here, 4,480 grams. And then I already figured out how many moles were inside of the cylinder. So you have to make sure that it makes sense. So that's how much it weighed and the gas weighed. They must have subtracted the outside of the cylinder already. And then we've got 160 moles. And so now I'm simply going to divide. I've got 4,480 divided by 160. And that gives me 28. Okay, and sometimes they'll ask too, if this is a diatomic molecule, for example, what gas do you think this could be? Well, what do we know has a molar mass of 28 grams per mole? Did you say nitrogen? If you did, you're right. So nitrogen N2 would be 14.0 times 2. So it possibly could be N2. It could be something else because it may not be one element. It could be a mixture, some type of gas. Okay. So what pressure, question 12, what pressure and torque will be exerted by 0.450 moles, so there's our N, of a gas at 25 degrees Celsius at 273, so we're going to get 298 Kelvin, if it's contained in a vessel whose volume is 0.65 liters. Okay, I like that we're not in milliliters, we're still in liters, so this is perfect. Okay, so again, I know that I'm looking for P in this situation equals nRT. So I'm going to write go ahead and set this up and let's see if you get the same answer as me, okay? You get 13,000 torr. Hopefully you did. So again, choosing my R, because they asked for the pressure in torr, I wanted to use the R value that matches that, the 62.4. And again, that's a constant, so that should be given to you. And so I got 12,873.6, but because of the two sig figs, then that would be 13,000, or you can say 1.3 times 10 to the fourth. And again, this is torr, which is the same thing as millimeters of mercury. Now, if you needed to convert, maybe for example, you were asked, you did the calculation already and you're like, oh shoot, I did this in torr. You don't have to redo the entire problem. So all you need to do is to convert the torr. So let's say I wanted atmospheres instead. So all I would do is I would set up a little bit of a bridge and I would say, okay, I know I'm trying to get rid of torr. And so I know that it's 760 millimeters of mercury or torr in 1 atmosphere. And so all I would do then is just simply divide it in order to get my, my answer switched. All right, last thing. So the last thing is called gas law stoichiometry, where it looks like you're using the ideal gas law, but then there's a twist to it, okay? So we remember that many chemical reactions we know involve gases, okay? So we've seen gases over and over again. If we know the pressure, the volume, the temperature of the reaction, we can carry out stoichiometric calculations to figure out how much of one substance we have when we know the amount of another. So anytime that's a situation, I always say that's when you need stoichiometry. Stoichiometry specifically figuring out how much of one when you know the amount of another, okay? And so we're going to use a ratio to be able to do that. So in this situation here, we've got substance A, for example, and we're trying to switch substance A to substance B. And we know that in order to do that, we need to use a mole bridge, okay? So the mole bridge is going to be our crossover from one to the other. So what we would do is we would try to get moles. So if we were in liters, we would get moles first, and then we would cross over to moles, and then we would get liters, okay, of the other gas. So remember, moles are your bridge over. Now, you could also do this with liters as long as you're using the balanced equation. The balanced equation does represent 3 things. The balanced equation, the coefficients represent moles, they represent liters, and they represent molecules, okay? But because people tend to be confused and they use grams, and which you never do, never, ever, ever do, I always like to say, just use moles. It's easy to remember, and it's easy to remember that it's a mole bridge, okay? But if you remember it, it could save you some time in some situations. So it says, if this is called gas law stoichiometry. Gas law stoichiometry. So again, figuring out one amount when we know another. When given conditions of STP, okay, if you are ever given conditions of STP, 22.4 liters per mole always works, okay? So if they say blah, 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 you're at STP now, well, as long as you're at STP, you can use 22.4 liters per mole, okay? So that's always going to be your molar volume if you're at STP. So if you look at this flow chart, it says, is it at STP? Yes. Well, all you're going to do is use 22.4 liters per mole, and you can simply use your stoichiometry that way, okay, and do a bridge. Now, if you're not at STP, which is going to be the situation here, then what you're going to do is you're going to check to see, I always like to see, can I solve it using Pivnert? If I can't solve it using Pivnert, then I need to use stoichiometry first, okay? So try to use Pivnert first, and then if you can't, do the stoichiometry and then come back and do Pivnert. But at least it'll already be set up, okay? So let's try these last 2 questions here. So we've got KBr and Cl2 is reacting with chlorine gas. And so the question's asking, how many milliliters of bromine? Now, it is really important that I know milliliters of what? What am I being asked for specifically? So they're giving me a temperature. Again, we always want to make sure that we switch it to Kelvin. So this is going to be plus 273. So we've got 298 Kelvin. We've got 105 kPa as our pressure. So there's our temperature. There's our pressure. And then they're giving us grams of the potassium bromide. Okay, so that's a little bit different because They're asking us for milliliters of bromine, but they're giving us grams of potassium bromide. Okay, so the first thing I want to do is I want to check to see if PIVNERT works. So I'm going to write PV equals nRT, and let's just see what happens, okay? So I know that I'm looking for milliliters of bromine, so I'm looking for volume. So that's fine, okay? I already know that I'm looking for volume. And then do I know my pressure? Well, it says that it's 105 kPa, so I'm going to write my pressure as 105 kPa. And then I don't know my volume. Okay, moles. Well, I've got a problem because I don't know moles. I know grams, but that's a potassium bromide. Okay, so I'm going to have to leave this empty for just a second here. So let's leave a little bit of a space there, okay? I could figure it out, I just don't know it yet. R, well, if I'm in 8 kPa, then I know that I want to use 8.31, and that's liters times kPa per Kelvin mole. And my temperature, I already figured out in Kelvin, is 298 Kelvin. Okay, well, since I don't know that, that means I actually need to do Stoich first, okay? So I'm going to take my 25 grams of KBr, I'm going to throw in a bridge, and if I add up the molar mass of it, I get 119.00, and that's the grams per mole. Always make sure you did this correctly and your units are canceling out. So I go to set up my equal sign here, but the only thing is, if I figure this out, that's moles of KBr. That doesn't work. I don't want moles of KBr. I want bromine. All of this is for bromine. So what I need to do instead is I need to do one more bridge here. Okay, now don't calculate it and you're going to waste your time. So all I'm going to do is I'm going to set up one more bridge. This is moles of KBr because I haven't switched that out yet. I'm trying to get to moles of bromine. Now, people will look at it and go, well, which one's bromine? I don't know which one has, well, it's Br2, it's this. It has to be one of the substances in the balanced equation. Otherwise, you can't do the stoichiometry. So this is Br2. And so if I look at my ratios, my coefficients, it's 1 of the Br2 and it's 2 of the KBr. So all I'm doing is simply looking at my coefficients there. Now I can calculate my moles. So then all I'm going to do is I'm going to work out 25 divided by the 119 and divided by 2, and I get 0.105 with 3 sig figs. And that's moles of Br2, which is exactly what I wanted. Now I can fill in my 0.105 moles right into that space, and very easy algebra now. So now I'm simply going to solve for my V, for my volume. So multiply everything on the right. So 0.105 times 8.31, and then times 298. And then remember, divide by what's attached. Same thing if you're cross multiplying. And I'm getting 2.48. And this is in liters. Now, just double check. They want milliliters. Ooh, see? Good thing I checked. So remember, big E small. If my unit's getting smaller, my number should be getting bigger by 3 places. So then that means that it's 2,480 milliliters would be my final answer. Okay, last one. So we're given another balanced equation reacting aluminum and oxygen. If Jeff uses 5 liters, that's my volume, of oxygen, so that's of oxygen, and negative 12 degrees Celsius, let's just make sure we get this right, negative 12 and the 273 is going to give me 261 Kelvin. So that's my temperature. There's my volume. I'm sorry, there's my pressure in millimeters of mercury. And then they're asking for grams of aluminum. Again, be careful. I see that my substance is changing. Anytime your substance changes, stoichiometry. Okay? All right, so let's figure this out. Again, what I'm going to do is I'm going to try to use PIVNERT first. So PV equals nRT. And so I know that I'm looking for grams, which grams isn't even in this equation, but that's okay. So let's fill in what we know. I've got 775 millimeters of mercury. My volume is 5 liters. Again, this is all for oxygen right now. My moles, I don't know, so that's N. My R, because I'm in millimeters of mercury, I'm going to use the 62.4 liters times millimeters of mercury per Kelvin mole. And my temperature is the 261 Kelvin. And so then, again, all I'm going to do is get N alone here. So 775 times 5 divided by the 62.4 divided by 261. And I'm getting 3 sig figs, 0.238 as my moles. N is 0.238 moles. But the only thing is, this is for oxygen, okay? I have not switched it to aluminum yet. That's all for oxygen. It says that's for the oxygen. So I know I need Stoich now. So I'm going to do my 0.238 moles of the oxygen, throw in a bridge. And now I'm going to do my moles of O2 compared to my moles of aluminum. And so that's my mole bridge. And I can see from my balanced equation that it's 4 moles of aluminum for every 3 moles of oxygen. So you have to use the actual substance, okay? So be careful with switching that. Now, I would think I'm done. Don't do the calculation yet. They want grams of aluminum. So one more step. So all I'm going to do is I've got my moles of aluminum. I'm going to switch it to grams. I use the periodic table. Aluminum is 26.9815. So let's just say 26.98. I think that should give us, because of sig figs anyway, we should be good to go with that. So 0.238 times 4 times 26.98 divided by 3. And I'm getting 8.56 grams of aluminum. And that would be your final answer. Okay. All right. So I hope you learned today a little bit about the ideal gas law with Avogadro's law. And then now, how do we incorporate gas law stoichiometry if our substance has changed and we want to still use Pivner? Okay. I hope this was helpful. Happy day, everyone.